Welcome back to your learning, everyone. Thank you for showing up. And let's carry on today with sinusoidal functions, periodic functions, and we're going to be connecting that with the material in our next unit. Very exciting stuff. So if you've come here to the Distance Learning Master Doc, you will have already gotten familiar with graphing sin x and cos x and Desmos, and we're going to take a brief look at some important instructions in there. You're going to be at home using Desmos a fair bit this week, particularly for periodic functions, periodic functions today. So that's key that you can get Desmos set up correctly. And then we're down here, and we're going to be looking at lessons on solving trigonometric functions graphically or algebraically. All right, and this video is going to treat graphical solutions. And then you'll be able to complete the exit ticket successfully. So the question that we're going to be looking at right now is, for what values of x does this function f of x is equal to cosine of 18 times x? For what values of x does cosine of 18x equal 1? Okay. So we're basically asking to solve this equation. 1 is equal to cosine of 18x. Okay. So to approach this graphically, first I would graph the parent function in Desmos. And so you're going to come over here, you're going to get yourself a Desmos window, and you're going to move your face over there so its face is not in the way. And then the first thing to do is go over here and adjust your scale. I know that when I have a k value of 18, when I'm multiplying my inputs by 18, I am going to be creating a period of 20, because 360 divided by 18 is 20. So this is going to create a function that will repeat every 20 x units. And I want to see quite a few x units, so I want to see at least up to, let's say, 120. Let's see, 10 periods here. And then the y-axis is set just fine because there's no change to the amplitude, so I'm going to see an amplitude of 1. So I could even zoom in a little bit on the y. So let's do that. Let's put that at 3 and that at -3, and that'll be just fine. Now, type in your function. One trick to typing functions in Desmos is, and the most important thing, change it to degrees, okay? Change your graph to degrees, okay? It will be set in radians to start. Set it to degrees, please. Okay, so Desmos does not like square brackets. So when you write in a function like this, write it as f of x is equal to cosine of bracket 18 times x. And there we have it. Just like we predicted, we'll see 1, 2, 3, 4, 5, 6, 6 full periods there. Did I say 10? That was just a simple math error on my part. Okay, so we see a fair number of cycles. Now, we know that we're looking for when does this function equal 1. So we could go over here and we could count them. 1, 2, 3, 4, 5, 6. And we can very clearly see a pattern in these numbers. The function's equal to 1 at 0, at 20, at 40, at 60, at 80, at 100, and then at 120, so on and so on. Okay? With more complex examples, it can help to use this trick. Write in your desired solution as a horizontal line, y equals 1, and then you will see all of the intersections. If you want to see all of the points listed in order, just go ahead and click them. And it will be very easy to analyze the pattern that you're seeing there. Okay, so that's a great way to see all of the different solutions. Now, you're going to go ahead and you're going to say, well, I now know what all the solutions are. All of them. Okay, they're going to be the multiples of 20. So I could say, in this case, that, let's go ahead and we'll use a blue violet pen. All right, so therefore, by graphing, we have found that we could write all of these solutions in the following way. And we're going to start using what's called sequence notation. So we're going to say that there is a series of terms. So we're going to call that t, and that it's a function of which number of the term that we're looking at. And we can write that as simply 20 multiplied by n. So what this is going to do And then we can also specify here that n is of the natural numbers, but actually more specifically, n is of the integers. So that means I can't put in like 2 over 3 here for n, because that's not an integer, just the number set, including 0, the negative numbers, and the positive numbers. And this will generate all the possible solutions. So when I have like, this could be written as like 0, comma, 20, comma, 40, comma, 60, comma, 80, and so on, right? This goes on forever, because this generates this list as I let n be different integers. It also generates it in that direction because I told you that n could be integers. Later on, we'll be looking at sequences where we definitely have a first term. Now this gives you a function that you could graph, right? And we could put that in here. And it would tell us that this term was the 0 term, boop, and it's one of our solutions. This one would put in a point at 20. This one would put in a point at 40, 60, 80, and so on. And so these are also giving us functions. Okay, so that's how you would solve a simpler example like that graphically. Let's take a look at a more challenging example. So now let's take a look at this situation where we have the same function, but now we're interested in when that equals a half. So we'll recall from our unit circle that we will get exact solutions when the following things happen. For cosine to be 1/2, if we have the unit circle here, we want this to be 1/2 of the, so this would be 1/2, and this would be 1. So this would give us the angle 60 degrees here. And it would be cosine of 60 degrees would be 1/2 over 1. We also know that this negative value here, this negative angle of negative 60 degrees, also has the cosine of 1/2 over 1. So we know that at cos 60 degrees and cosine of 300 degrees, which is negative 60 degrees, these would be the two things that give us a solution. But also, if we add 360 to either of those, so 420 degrees would have a cosine of 1/2, as would 660 degrees, and so on, as we add and add and add 360 degrees. And that's why when we go ahead and here, we change our desired solution to y is equal to 1/2, we'll see all of those. There's negative 60 degrees, but because we have this 18 here, that's now negative 3 1/3. Because if I multiply 18 by negative 3 1/3, that will give us 60. Okay, negative 60. And then the same thing over here, 3 1/3 there. So now we can still create an expression, an arithmetic series that gives us all the possible solutions. And let's start from here, 3.333. We saw up here that this function has a period of 20. So if I add the period to that 3.3, I should find another solution over here at 23.3. And then I'll find another solution here at 43.3 and 63.3 and 83.3, all of these different points, all separated by the period. They're all separated by 20, and they all have this 3 1/3 added to them. All right, so we can express that set of solutions as a function, or sorry, as a arithmetic series. All right, and that's going to look like this. By graphing, we have found that if we write this as, let me just get a much smaller pen there. This one is good. Okay, that if we wrote this as the term is a function of n, and that's going to give us, the first one is 3 1/3 plus 20 times n. This will generate that list of solutions, okay? And when n is of the integers. All right, and let's take a look back at our graph. That gave us all of those numbers, but we missed these ones. We did not have these solutions here. This one, this one, this one, this one. These are all 20 minus 3 and a third, 40 minus 3 and a third, 60 minus 3 and a third. Okay? So we can write a second arithmetic series that are also solutions to this equation. So let's go ahead and put those in. And we could say, we could call this one then t prime, t1, and this one t2 of n. And then this one would be negative 3 and 1/3 plus 20n. And that would be then a different series, and is still, of course, of the integers. And that would give us a different series of numbers, but they would equally be solutions. So this is one way to express the multiple solutions we can get from these types of equations that we find by graphing. All right, now let's take a look at one more example with a fully transformed function that has an a and a c value and a d value as well. So now let's take a look at, let's type that in together. Let's take a look at this example where we have now g of x is equal to 2 multiplied by sine 9 of x minus 5 minus 1. Notice I'm not using square brackets here because Desmos doesn't like them, so just use round brackets. Okay, so let's type this one into Desmos, and I'll show you how you want to type it in. So I would start by writing g of x is equal to sine x. And then notice that we have a very long function that starts at the midpoint and rises, which is what we expect from sine. Its value at 0 is 0. And then go ahead and put in your k. So you're going to put a bracket around this and say 9 bracket x bracket. Okay. And then we see we have changed the period. We squeezed it horizontally, compressed it. And then you can add in your c, which is minus 1. And I say, okay, let's also add in our a. That's going to stretch it that way. Cool. Okay, and now we're starting to see, okay, here are that minus, this is that minus 3 that we were looking for as a solution. I'm seeing a pattern already, but let's not forget to put in our phase shift. So we were asked to do x minus 5, if I remember correctly. X minus 5. And then just verify. Do we have that there? Yeah. And then notice that when we said minus 5, it actually shifted the whole function towards the right, towards the positive direction by 5. So this midpoint, which used to be over there before we added in this d value, is now right here. Okay, that's the horizontal axis there at negative 1 to 5. Okay, these two numbers show up there, which was the old starting point. Now, we want to answer this question, when does this function equal minus 3? We can go ahead and find all of those solutions down there. Let's talk about them. Here we have 35 minus 3, 75 minus 3, and 115 minus 3. So maybe that's a little tricky. So what we can do is go back here and write those down. And we'll write these down as the first, second, and third terms in an arithmetic series. 35, 75, 115. Okay, I can remember that. So we're going to write this down this way. Going to create a little table. And we're going to have n and t of n. Okay, this is going to be the number of the term. This is the value of the term. So 1, 2, 3, 35, 75, and 115. Okay, now what we're going to extract from that is we're going to find these values that we need to create this arithmetic term. So for any like arithmetic series, some t of n, you're going to have some initial value plus something multiplying that value. And when we're working with arithmetic series, our general form for that is going to be a plus, he says checking the letters we use, n minus 1 times d. Okay, where a is the starting term. That's our T1, okay? And D is the common difference. Notice that this is not D, the transformation value. This is not A, the transformation value. We're just borrowing those same letters to match the textbook. Okay, so, but here we know the A, well, that's T n is 35. Okay, and the D is the common difference. We can see that these are growing by 40 at each time. And we can look at this 9 should be giving us a period of 40. So watch, if I know that 9 is K, let's find the period. So the period is equal to 360 divided by K, which is 9 in this case. That's equal to 40. Okay, so that gives us the common difference, and we see that there. Mathematically, you would just take that 35, use it for A, and then subtract this from this to get n minus 1, or sorry, to get D, and then you would multiply this to get to your nth term. Okay, so therefore, we can say that when we have the series T of n is equal to 35, which is our first term, plus n minus 1 times 40. Okay, and that's going to generate all of the possible solutions to this equation. In fact, we don't need n minus 1 in this case. We could just say n times 40 or 40n, and that would still generate the infinite list. It just depends on which term you're counting as the first or the second. In this case, it doesn't matter, but in the examples we'll look at soon, it will, and we'll use n minus 1. All right, now let's look at the more challenging situation of when y is equal to 0. And we're generating multiple solutions here. Again, we've got those 3 1/3. That's just a coincidence. And we want to generate a list that will give us all of these. So let's see how we can do that. Okay, so we're down here. Just going to move that up. Okay, oh, too far, Mr. Jennings. There you go. Now let's make this a little bigger. All right. Okay, so for this function, for what value says it equals 0? Well, we're going to need 2 lists again, because taken together, they don't make an arithmetic series, because there's not a common difference. You notice it jumps by a small amount and then jumps by a big amount, jumps by a small amount, jumps by a big amount. So we'll make 2 different lists, and taken together, they give us the infinite set of solutions. All right, so let's take a look at that. So here we go. We know that the first list is going to be, I'll just turn these ones off, doot, doot, and doot. We want 8.3, 48.3, 88.3. Again, we're seeing that same common difference of 40. Doesn't matter which set of solutions we're looking for here, the period is always 40 of this function. So that's great. So let's write our terms. We have T of n, and we'll call this T1 of n, is equal to 8 1/3 plus 40 times n, 40n, and that will generate one list. The next list, T2 of n is equal to, well, let's go ahead and grab our first term, and this is arbitrary. We could arbitrarily choose this one, 21 2/3. Okay, let's use 21 2/3. If anyone is saying, Mr. Jennings, how do you know that that's 21 1/3, or that's 8 and 21 2/3, or that's 8 and a single third? Well, 1/3 is equal to 3 repeating, okay? And 2/3 is equal to 6 repeating. So over here, I see that this is 21 and 6, 6, 6, 6, 6, 6, 6, and then they have to round up to a 7. Okay, so that's why we're getting, that's how we know. Okay, in case that's news to you. Okay, so now let's take a look at this list. 21 2/3 is our first term. So write it down. Oh, use the pencil in the right way. 21 2/3 plus 40n. That will generate the other list. Okay, so there we go. Those are all the possible values of x where g of x equals 0. Okay, and so that's how you would solve these types of problems using a graphical method. A little bit straightforward, isn't it? Okay, so welcome back, everyone. Reviewing your knowledge of transformations of functions and connecting that to the arithmetic series that's generated by this period here, in this case 40, in the previous case 20. Bye for now. Oh, and definitely hit me up in the chat or by email with any questions you might have.